Geology is really cool. There's so much going on around the world. Like even today, there was a magnitude 5 earthquake in Indonesia, in Sulawesi. It's an island in the Indonesian archipelago. And also today, the volcano Kilauea is still erupting. There's a big fountain essentially that's going off in Hali Mau Mau, which is the central crater in the Kilauea caldera. So kind of neat to have these sort of activities going on. There's always something going on around the world. So what I wanted to do for you actually is to show you what is going on around the world as far as geology is concerned. So in some of the supplemental materials that you'll find in Blackboard, I made a link in there to something called Earth Week. It's a diary of the planet. And so week by week, they go into, I think last week was, well, actually it ends today or yesterday. They tell us what's going on around the world. So without further ado, I'm going to give you a short tour of what geology is like and what types of things we're going to be covering in here, at least in a little detail. And then we're going to get into the specifics next. And so I go into the big picture about the universe, using the E equals mc squared, but then eventually we're going to wind back around to atoms and elements and what makes up an atom and what is ionic bonding, covalent bonding. So that's going to be in the next presentation after this. So these rocks are actually ancient, absolutely ancient. So they were deposited in a shallow, well, fairly deep basin actually on what today is a mountain range, but of course the mountains have come up since those rocks were deposited. When they were originally deposited, that was about, I guess, let's see, 900 million years ago, maybe 1.1 even. It goes way back, 1.1 billion years ago. There are no fossils in it that I've ever seen, other than the fact that every once in a while you see some stromatolites deposited in here. Well, stromatolites are really kind of ancient creatures. They're like a bacterium that would secrete slime and trap sediment. And so it traps it in funny sort of shapes. And they're responsible for the earliest, atmosphere on this planet. So stromatolites are really pretty important in that. But the cool thing in this area is that the stromatolites, which are made out of carbonate rocks, and carbonate rocks are kind of a proxy for saying that a climate was pretty nice, pretty tropical. Today, for instance, when we think of carbonate rocks, they're being deposited in the Middle East and let's say the Red Sea or also the Persian Gulf on the other side of the Arabian Peninsula. But then also you get carbonates in the Caribbean, right? And so carbonates there and then carbonates also in the South Pacific. So that's the sort of place where you get carbonates. It means it was pretty nice weather, if you will, back 1.1 billion years ago. And interpadded with those stromatolites are actually some rocks that were deposited by glaciers. So it alternated in between times when there was really nice tropical weather and all of a sudden glaciation, then tropical weather and then glaciation. And it alternated between those quite a lot in this interval. And these are rocks that actually preserve that sort of signature, if you will. So in other words, we can learn a lot about the ancient past. Now, this is really ancient past when you get to 1.1 billion years ago. But we know that climate change existed back then, and then some of the earliest glaciations occurred back then. It was a time period called the Neoproterozoic, in fact, and so really pretty spectacular. And so we use our knowledge of where carbonates are being deposited today and where we see glacial deposits being deposited around glaciers, obviously, today. But we know what they look like in the ancient rocks because the glaciers are long gone. But the rocks that they left behind are still there. So they're called glacial diamictites, actually, is what the term is. Not something that you need to know about, but what you do need to know about is geology is one of the best tools that we have for understanding climate change, especially when we talk about ancient climate changes. So if geology is related to ancient climate change, it's also related to the physics behind it. And so this is where I like to point out that Einstein can even be applied in geology, at least in a way. He came up with the theory of relativity. Actually, there's two theories of relativity, and I keep forgetting which one's which, but there's a specific one, and then there's one that's more general theory of relativity. one of those addresses this issue, the very famous equation that all students tend to learn, E is equal to mc squared. Now, E is equal to energy. That's what E stands for, the capital E. M stands for mass, and C stands for the speed of light. And of course, it's squared. And so that means it's going really fast. So matter times the speed of light squared is equal to energy. And so we, for the longest time, lived under these sort of like circumstances of our groundwork, our cumulative knowledge of science was that was how things worked. And it was only about 20 years ago or so that people began to question whether, this functionality in between quantum science and then other types of science, the more qualitative types of science that people do. So quanta kind of introduced a new variable into the equation, you could say, and people began to realize that maybe there are other dimensions that we just can't detect or we don't see. And so, in fact, people call that string theory, and string theory says that there may be up to 11 or 10 at least different types of dimensions that we really don't even see, and that maybe that's where gravity comes from. So, and they've tried to test this, right? So they build these huge particle accelerators and they smash things like protons into other protons or other particles of some sort. And then they try to determine how much energy was given off by those things. And it was only in the last couple of years that they were able to determine, there was a postulation out there that there was this thing called a Higgs field, that you could actually have something come back from these other dimensions and pop into our dimension, and that was the Higgs boson that they were able to make essentially out of nothing, which at least they detected the energy that's associated with it. And, these are things that, I'm not particularly well versed in or anything like that, but at the same time, it's nice to know that we don't know everything. But in fact, what we do in geology is we take the energy and the mass, and we study those sort of things a little bit anyway, at least energy resources and things like that, things that get converted to energy. And then we also study the rocks and things like that. And so, in fact, this is just kind of an introduction, because when we really talk about this sort of stuff, we're talking about what is there's a lot of big questions, right? What is the origin of Earth? Or what is the origin of our solar system? Where did we come from? Where did humans come from? And so those big questions, geology can help address, actually, which is kind of neat. So for the origin of the solar system, anyway, we have to go back 4.56 billion years ago in order to determine what happened back then. And of course, there's not very many rocks that are left from back then. In fact, there are no rocks that date back to 4.5 on Earth anyway, but there are some, meteorites that come into Earth and land, and they were able to date those, and a lot of those show us the age of the solar system, and that's 4.56. The actual oldest material on Earth that's ever been found is 4.4 billion years old. Earth-made material, I should say, that didn't come from outer space and land here. So 4.4 billion years ago, there was a little tiny crystal of zircon, it's called. That's the mineral name anyway. It's made out of zirconium, and then also some silicate minerals, so silicon and oxygen with it as well. Well, we're gonna talk a little bit about chemistry in here as well. So we branch out into other sciences as well. But when we talk about the beginning of the universe, we're talking about 13.7 billion years ago. So in fact, the Earth is made out of recycled material that was part of other stars at one time. Those stars lived, died, blew up, whatever. They left some dust behind, and that dust gathered together, and it formed our solar system. And so our solar system is a result of a combination, some people have estimated, of at least 5 stars came together. So the dust, self-gravitation brought it all together in a spinning disk, and sure enough of the primordial gases of hydrogen were left behind that the center fused and formed our sun. I spend a lot more time in this when we talk about it in historical geology, but for here, just know that once upon a time, it sounds like a fairy tale, but it's not. 4.5 billion years ago, the Earth was formed roughly at the same time that the sun ignited. And but the sun's a recycled star. Know that. So there are about 200 billion stars in our galaxy. We're just one of 200 billion galaxies. And so, I mean, we're really close to some other galaxies like Andromeda, a few 100 million years from now, we're going to collide with Andromeda, but I don't think I'll be worrying about it at night. So if the universe is, 3 times older than the Earth and the solar system, how did that happen? And so that's what they call the Big Bang, obviously. And you guys have heard all that before, right? It's like, well, we don't know what it came from. It was just what they call a singularity. And then all of a sudden there was a universe. And then all of the laws and the principles that govern the way that our universe operates occurred within that earliest time frame. And so finally things cooled down enough. But at the same time, we're actually still expanding. And so the universe is expanding. And some people think that we're not even the only universe. All of the galaxies that we know of, when we train a telescope back into the night sky and look as far back as we possibly can, that's about 11 billion years ago. Not quite to where, that we can get back all the way to the Big Bang, but we can hear the noise from the Big Bang kind of still. In the far distance, it's a hiss that is in radio telescopes. And but the first galaxies, would have showed up not too far after that Big Bang. And we're one of these galaxies. So the Milky Way is one of these galaxies. We're probably a combination of several galaxies that have collided over the billions of years that the universe has been in existence here. When people try to map that universe, it's hard to describe. It's kind of like a bubble, but it's expanding in all directions, and everything is speeding away from us. Astronomers know about something called the red shift, and so many of the stars that we can train a telescope on, there's an actual shift that these things, like a Doppler effect, like if you're listening to music of a car that's going down the street, it seems to get farther and farther away. It kind of stretches out the sound a little bit, and so that's the sort of thing that happens when you get the red shift, when you look at other stars around us here. So astronomy is kind of related with, the geology science too. And so, but this is physics here. And so when they map these sort of things, they can do it with radio telescopes, and it's splotchy, but that's kind of a picture of what they like to represent the universe as. So the next slide shows you what some of the early galaxies would have looked like. And so this is from the Hubble telescope, and they make estimates then from that. And of course, these are galaxies that are so far in deep space that it took 11 billion years for their light just to get to us. And so we can collect that with a telescope. And, some of those galaxies are probably gone right now, or they formed other galaxies, but we don't have the light from those galaxies now. So those are the ones that we're able to train upon. When you look farther and farther away in the night sky and deeper into space, you're going back in time as well, because it takes time, the speed of light, for that light to get to us. So it's really a fascinating sort of study in astronomy. But the whole reason I'm framing it this way is because we live in one galaxy. We'll never get out of this galaxy as far as we know. And we have 200 billion companion stars that were going around the center of this spiral galaxy. We're in one of the arms of that galaxy. And there's at least 4,000 exoplanets that are around it. I told you 3,000 in the last lecture, I think, but there's actually 4,160. I try to update that, and there may be just a few more now. And they're finding out lots about these things. Sometimes planets don't even have stars around them. They're rogue planets. They were cast out of some other solar system, and they wander across space. And sometimes they do that in pairs. And so here you can see, well, this is a snapshot of another galaxy. We can't look at the Milky Way except from Earth, looking upward, and we can see it edge on, essentially. So that's what the Milky Way is. It's the side view of our galaxy. And there's lots of dust and things like that kind of obscure our vision of it. But in this other spiral galaxy that's in this photograph, you can see that there's an uneven distribution of stars in there, but know that there's a lot of planets. There's a ton of planets, and so it gives one hope that, maybe there's life somewhere else. Who knows? We're such long distances away. We may or we may not be able to see these other places at some point, but there's always hope, I guess. We're going to zoom in now. So for like the Milky Way, here's the solar system, at least a depiction of the solar system, not to scale, obviously. If it were to scale and the Earth was like the size of a a head of a pin, it would take like 4 or 5 miles to put all the other um, planets in relative um, uh, uh, how close they are to one another, in proximity to one another. It would take miles if the Earth was the size of a head of a pin. And the sun would be, I think, the size of a basketball, I think is what they say. But here you can see that depiction of Mercury, Venus, Earth, and Mars. That's the interterrestrial planets. We call them that because they're made out of rock. The ones that are farther out, there's 4 of them. There's Jupiter, Saturn. Saturn has the rings, obviously. Uranus has rings also. So Uranus and then also Neptune is out there. So that's the 8 planets. Used to be 9, right? But they demoted Pluto because Pluto's essentially an ice ball, a dirty snowball, if you will, even though it has moon. It has 2 moons, I think. But there are other planets besides the 8. We call that one a minor planet, actually. And so the minor planets, or dwarf planets, they call them also. There's one that's orbiting inside of Jupiter. It's like 100 kilometers across, I think, at least. It's Ceres. It's a really large asteroid is what it is, but it's bigger than some of the moons. I think, in fact, it's probably bigger than one of the moons on Mars. Mars has 2 moons. So you can see here some of the names for some of the minor planets that are also in our solar system. They're still, traveling along with us. We're all trying to catch up to the sun, then we whip around it, It's really a fascinating sort of like study to be able to look at, the planets and astronomy and so forth. But for this class, we're going to focus in on Earth. And of course, Earth, 4.56 billion years old. What I'd like to do is to maybe show you some snapshots. I like showing photographs of places. So we're going to start with the Bahamas first. And the Bahamas represent that sort of carbonate sedimentation that we talked about with the stromatolites. In fact, there are some stromatolites that are in the Bahamas. The Bahamas, you can see, are the very light blue, that kind of cyan blue, just off the coast of Florida, in between Cuba and Florida there, just a little bit to the east of that. That's the Great Bahama Bank. And it's absolutely beautiful. The water is that color as well. I've been working in Jamaica over the last 3 or 4 years now, and the water there is pretty close to that in a few places, but it's just actually stellar. It's just, when you look at it, it's turquoise blue. But these carbonate banks tell us a lot about the way that past climates have influenced the Earth and how they influence the living creatures on Earth. Carbonates, as it turns out, and living creatures go hand in hand. So most carbonates are a product or a result of some sort of pumping out of carbon dioxide out of the atmosphere. And of course, plants do that. The other thing that you see here is kind of cool. There's some like gash-like areas. And so you can see actually a microplate in between Jamaica and Cuba there. And on the north side of Puerto Rico, which is up to the northeast, it's on the Caribbean plate there. That's one of the plates we're going to talk about when we talk about plate tectonics. So the Caribbean plate is defined by volcanoes on the right-hand side. They're called the Lesser Antilles, the small islands on the east side there. And on the west side, there's a series of volcanoes as well in Central America, in places like Nicaragua. Lots of volcanoes in that area, and some even in Costa Rica and so forth. So that plate is experiencing subduction. It is experiencing subduction on both sides. So in other words, some of the ocean crust is being gobbled up and reincorporated into the mantle in those locations. To the north, there's a new crustal area. That's the Gonov plate that's being formed in between Cuba and Jamaica there. And so that's a new plate that's opened up there. And there's a spreading center in the middle of that where new crustal material is being added to that microplate. That's a trench actually on the north side of Puerto Rico there, but it's not subduction that's going on there. It's actually strike slip motion. In other words, it's sliding side by side there. And so Cuba is going, let's see, let me get it right here. I think Cuba is going to the left and Jamaica is going to the right there, if I recall correctly anyway. But we're going to zoom in a little bit. But we're going to go into the Bahamas, though. So we're going to go to the Bahamas instead. So the next time I zoom in here, you can see these beautiful, beautiful dunes. in that turquoise blue water. So they're just slightly underwater, gives them that blue cast like that. But most carbonates are white in color like that. And so you're actually seeing the color of the water around them there. We zoom in a little bit more, you can see what those dunes are made out of. They're little tiny carbonate sand grains, essentially, and they're called ooids. Ooids are like little egg-shaped, that's where the term comes from, egg-shaped ooid. And so you've probably heard the term ova before. So the ova makes eggs. And so these are little tiny eggs-like things. So they're not really eggs, but they're shaped like eggs. And they roll around on the seafloor. And they gather coatings as though they were some sort of like candy, like a jawbreaker. A jawbreaker, if you've ever bitten into one, there are these candies that you suck on and everything, but they have layers built up on them. Well, these ooids have layers as well. And you can see one that's been cut in half there and sliced open, and there's a fecal pellet in the middle of it, actually, right there, like a fish or some snail pellet or something like that. But then layers of carbonate grow around it, and that's actually the mineral aragonite, which has the chemical formula of CaCO3. It's a chemical precipitate on the outside of that fecal pellet. If we zoom in a little bit more, you'd be able to see that each one of those layers is discrete. And so those are the things that make up part of the Great Bahama Bank. They occur every time you get a lot of wave agitation and you get, pretty clean water, no clays or anything like that in it, these things will form. Okay, so now let me give you the funny part here. Funny part in the sense that it's ironic or astonishing. They find those actually in Springfield. They find ooids. Yeah, they find ooids in Springfield. Well, there's no seas that cover this landscape now, but there was at one time, and they were shallow seas and wave agitated, and so ooids formed here, right in Springfield. And in fact, it formed all across Missouri pretty much. It's a rock unit we call the Short Creek oolite. Now, oolite is a rock body that's made out of ooids. And so if you were to drive to the intersection of Kansas Expressway and Bennett Street, you would see in outcrop there some of these ooids. We call it ooid grainstone, but it's really a fascinating sort of type of rock. So it tells us a little bit about the rocks in Springfield as well. We were not only shallow water they accumulated, these ooids accumulated in little sand dunes in Springfield at that time. And shallow water, when shallow seas covered this landscape, you know that also because we find lots of fossils in this area. Now, it dates back about 340 million years ago, but it's what happened here. And it was a different climate in this place. Well, the climate changed mostly because we have drifted away from where we think we were. We were at equatorial latitudes back then. So even Missouri, this part of North America, was at equatorial latitudes at some time in the past. So that's what a limestone can tell us about. And so that's kind of neat. The next place we're going to go is to the Grand Canyon. Now, this is one of my favorite places on Earth. So the Grand Canyon, if you look at this photo here, this is a beautiful shot. In the far distance, at the horizon, you can actually see some blue outlines of mountains. That's actually, they're called the San Francisco Peaks. It's really close to Flagstaff, Arizona. And so this photo was taken by me looking across the Grand Canyon, looking at those volcanoes in the far distance. And they're still active, they haven't gone off for a few thousand years, but it's not been that many years ago that they were active. Like, Native Americans were living up close to Flagstaff, Arizona, when one of those volcanoes went off. Today, it's a national monument. It's called Sunset Crater. So when Sunset Crater went off, it actually buried one of the Native American towns that was around and some adobes that were in there. So these were the early ancestors of the Hopi Hopi tribe. It wasn't a reservation back then. This was their land. This is the Grand Canyon, however. And so what you're looking at in the far distance, those are really recent volcanoes. And then what you see here in the close distance here, that's a limestone again. The white rock here on the foreground is what they call the Kaibab limestone. Now, it dates back about 270, 280 million years or so. It's a little bit younger than the rocks around Springfield, but If you wanted to see rocks that were equivalent to the rocks around Springfield, you'd have to go deeper into the canyon to see it. And in fact, it's called the Red Wall limestone. And you can just barely see it where the shadow is kind of there. There's a cliff, a sharp cliff there that forms the Red Wall limestone. So the Red Wall limestone, Mississippian in age, same age as the rocks here in Missouri. In between that, there's these red sandstones. And so those are assigned to a rock unit that's called the Supai Formation, actually the Supai Group. And at the top of that, it's a little sandstone called the Coconino. So, both of these, and even the Kaibab limestone. Kaibab limestone is Permian in age. Those all predate the dinosaurs. But if you're to go deeper in the canyon, you get deeper and deeper back in time, and eventually you're going to get back to some of those Precambrian rocks that would date roughly 1.4 billion years ago, and then some of the rocks that are equivalent to the rocks around the Salmon River. And so those are a little bit farther to the east from where this photograph was taken, but that is a photograph of the Grand Canyon. So we love exposures like this as geologists because we read them like a book. It's as though you could page through the chapters in the history of the Earth by going to these exposures, these outcrops. And so this canyon exposure here, this canyon outcrop, tells us about the geologic history all the way from 1.4 billion years ago all the way up to 200 and some million years ago. And so it's really quite a story. And so geologists read the rocks like they're looking at a book. And the rocks tell us stories essentially, but we have to help them interpret it. And we apply science when we try to figure out is like, okay, what's the correct story? And how do we describe and how do we bring into our understanding how these rocks formed? Really quite an amazing sort of story that geology has to tell. Now the next photograph is kind of like some new technology that was applied to these rocks. You can see the Grand Canyon here in a digital elevation model. Now digital elevation models kind of map the surface. It's like a 3D map, if you will. And the canyon is in the green area there, but the high spots, that's the Kaibab monocline actually right there that's in the purple. It's kind of a part of the southern part of what they call the Aquarius Plateau. So where the photograph was taken was roughly... yeah, you can see a kind of a canyon that's right at the edge of where that purple was, where it turns fuchsia, right in that area. That's where the visitor center is on the north side of the Grand Canyon. And the south side of the Grand Canyon, you don't get much of it there, but the volcano is a little bit farther to the south. Now, when we understand that canyon, the canyon had to have formed after those rocks were deposited. So those rocks were deposited first, and then at some point a river cut through there. And not only did it cut through there, the land rose around it and the river kept cutting downward. And so the history of that's a little perplexing because so people are still trying to figure it out. Is it really an old canyon or is it really kind of young and that river's just cut into it recently? Well, as it turns out, one of the most recent ideas about how this canyon was cut, that it could have been cut by a river that was heading east. Now today we know that the Colorado River cuts through there and is heading west. It occupied that older canyon essentially when it came through, and today it cuts across the west side of Arizona and heads out into the Gulf of California, Sea of Cortez, and that area in Mexico. And so really a fascinating sort of place. So if you read the literature about when this thing formed, it varies between 600 million years ago when the canyon began to form. Well, no, not 600. That's way too far. 60 million years ago. Or it could be as young as like 16 million years ago or 8 million years ago. So people are still studying that. And so they're trying to figure out the age of that canyon. Not everything's been solved in geology. There's still stuff to work on. The next stop on our list here is we're going to go to the Middle East. We're going to go to southwestern Asia, essentially, and to Iran. And Iran has some of the most rugged landscape you can imagine. And right next to the Persian Gulf, there's a whole series of mountains there. They're buckled up. And the whole reason for that is because Africa was a huge plate at one time, except Africa kind of is beginning to break apart. And when it broke apart originally, the Arabian Peninsula began to drift away and head north, essentially. And so the Red Sea is forming today and widening today because it's a spreading center. And so it's kind of pushing, or maybe Saudi Arabia is being pulled under Iran, essentially, and because they're colliding with one another, you get these mountains that form like this. Now, these mountains that you see they're called the Zagros Mountains, and they're folded into a series of, well, literally they're called folds in geology. And we have two different kinds of folds that we recognize. We call them anticlines or synclines. You're going to get that later anyway. But anticlines are what these are. They're upfolded sort of layers of strata. And because they were upfolded, there were some slightly less dense rocks that were at depth. And they're made out of salt, essentially some salt. And that salt began to push through that anticline. So low density materials was making it low density material. These salt, they're really, they call them salt domes. And these domes began to push upward in these anticlines. And they pushed through, in fact. And so then they began to spill out over the landscape. They call them salt glaciers, actually, of all things. So you can actually see where some of these salt glaciers have pushed through. And the interesting thing about it is they don't look white like salt does. They look dark, right? So they're dark because they have a lot of petroleum in them. They have a lot of organic material that's in them. And so Iran, just like Saudi Arabia, has a lot of oil and gas. And so that's one of the resources that they can tap into in this sort of place. And so they look around these salt domes like this and these salt diapirs. Diapir is the same thing as punching through something. On the next photograph here, you can actually see it up close here, and you can see the direction that the Saudi Arabian Peninsula, that Saudi Arabian plate, is heading. And it's actually pointing to the north kind of there, and you can see where Iran is being indented upon there, and you can see the arrow points to where those mountains were in the last photograph here. And so it explains why we get these sort of things like, well, folds in some of these rocks. They're slowly being deformed. Weird thing is, rocks can flow. You just learned that, right? So they can flow either as diapirs, or they can kind of bend as well and form things like anticlines and synclines. And that's a really neat part of geology. It's called structural geology. And the idea that we can take the plates and break them apart and move them around, that's called plate tectonics. That's the theory of plate tectonics. So as we go next on the list here, we're going to stop in the Hawaiian Islands, and you can see Pu'u'o'u. It's one of the vents in Hawaii where there's volcanic activity. The most recent volcanic activity, however, is in a place called Halemaumau, where all of the Kilauea caldera is filling with lava again and still erupting actually right now. And so I'm going to show you some images of that as well. That's not in the presentation that I'm looking at right now, but it will be. And so, but Pu'u'o'u is the one that exploded just a couple or 3 years ago and kind of ruined some houses and things like that. But it didn't kill anybody as far as I know. As it turns out, all of the Hawaiian Islands are part of a volcanic chain that stretches all the way up to Alaska. Now, most of them are submerged, and they call them seamounts now, and they're not active at all. But there's active volcanoes going on in, on the big island of Hawaii, but then also on Maui. Maui is adjacent to it, and it's got a Haleakala is the name of the mountain on Maui, and it's still steaming at the top. It's 11,000 feet high. That gives you an idea of how recent that volcanic activity occurs, because when volcanoes grow, they add elevation. When they get older and begin to weather, they get shorter and shorter. And so that's what you see in the far distance. And so on Molokai, it's not nearly so high. And then when you get even farther out to Kauai and to Oahu and then to Kauai, the islands are much shorter. But they're all made out of volcanic rock. And so that's kind of cool. So these volcanoes, in this case, are due to what we call a hotspot. And a hotspot is sitting on top of the mantle, at the mantle where there's a pool of hot material there. And it punches through and causes these volcanoes to erupt there. The next stop on our list of things that can happen on Earth, things that are kind of cool and processes that operate. You see that ring in there? That's from a meteorite impact. That was huge. It was a big thing that happened about 215 million years ago. And when it hit, it left behind this central uplift. And so just kind of like a milk drop. You ever seen photographs of milk dropping and then rebounding upward? That's kind of what happens with meteorite impacts as well. They're hypervelocity impacts, and so they impart a lot of energy into the Earth. A little bit more physics for those of you who are interested, not test material, in other words. The amount of energy, the kinetic energy that's associated with impacts, is 1/2 mv squared. 1/2 of the mass times the velocity squared. So it's a little bit like E equals mc squared sort of equation, right? Except a few bit different sorts of pieces to it. So 1/2 mv squared is equal to kinetic energy imparted by impacts. Now, most of the impacts are pretty small, right? So this one they estimate to be, oh gosh, it's 100 kilometers across. So it would have been about 10 kilometers, the impactor itself. So in other words, if I had a globe and a sand grain next to it, the sand grain would be about the size of the impactor that hit, and it left behind that structure. So that's 100 kilometers across. We're in a cosmic shooting gallery. It's just the way it is. Okay, so we have meteorites across the Earth's path all the time, and every once in a while they hit the Earth. I'm pretty sure you would know about the dinosaurs were wiped out. Most of the dinosaurs were wiped out by a large meteorite impact. The one impact that wiped out the dinosaurs would have been 66 million years ago. And so the dinosaurs occurred after the Permian. And actually, nobody knows exactly what caused the Permian extinctions, but that was the largest extinction on Earth. And the second largest that we know of is this, they call it the KPG boundary now. So it's the Cretaceous-Paleogene boundary. And it would have wiped out the non-avian dinosaurs. The birds are still with us, however, and they are related to the dinosaurs. But that's what happened here as well, 215 million years ago. Here's an artist illustration for what happened at the KPG boundary. We know where that hit actually now, and that's in the Chicxulub Peninsula. That peninsula is in the easternmost part of Mexico. And so really a fascinating sort of narrative that goes along with this, but it's the science that builds these narratives, however. You can't let imagination run away with you and say, oh, there must have been an impact there just because, for instance, with the Permian boundary. Not necessarily. That also was a time when there was massive outpouring of lavas across parts of the world as well. Okay, next on the list here is the Sahara Desert. Sahara Desert is still with us, of course, but you may not have known this, but there were once lakes in the Sahara. That would have been during the last ice age, so like maybe somewhere between 1.5 million years ago up until about 12,000 years ago, various lakes in that area. And some of those lakes are actually still drying out. So like Lake Chad is in the country of Chad. And so there's this sort of phenomena that eventually there was a desertification after the last ice age. And so that desertification led to these sand dunes. And so the Sahara is the largest sand-covered area across the entire world, with the secondary smaller ones being in Central Asia, like the Gobi Desert, or in Western Australia. But these sand dunes like this, believe it or not, have a worldwide impact. What happens is, of course, the winds blow, and it carries the finer particles, the grains that are finer than sand grains, and it carries them out across the ocean. In fact, you can see in the satellite image, you can see where that dust is being carried off the continent of Africa, and it's going to wind up being deposited over in North America, in fact, and the Caribbean especially has a lot of this sand accumulating in places. Now, ironically, it's not the only thing that travels on the winds like this. If you can pick up a silt grain and carry it across the entirety of the Atlantic, you can also carry things like viruses. And so some viruses have actually been picked up in these winds and carried. Now, they're not the kind of viruses that affect humans, but they're the kind of viruses that affect sea life. And so some sea life is impacted by these dust clouds that are blowing off the Sahara. Why do I even mention that? It's a geologic process by which deserts form and by which winds carry those materials across the oceans, called aeolian processes, wind-blown processes. And so it's a story of sediment transport as well. And so that's an important aspect of geology too, and as well as understanding and seeing how they impact things like the Bahamas. Well, the Bahamas get this dust, and so it's actually killing off some of the sea pens that live in the Bahamas. They're a type of soft-bodied organism that lives on the seafloors there. So the last one we have here, I think is the last slide, one of the last slides anyway. This is to show you one of the largest living organisms, creatures, I guess you could say, in the world. That's not really an organism, but at the same time, it's one of the features you can see from outer space. It's part of the Well, it's the Great Barrier Reef in Australia. Now, it's a series of separate reefs that are all, if you want to link them all together, you'd call it the Great Barrier Reef. And they're really close together. They're like little little atolls, if you will, or little islands almost that stretch all the way from the northeastern part of Australia all the way to the southeastern part. Most of that eastern coastline of Australia has corals on it like this. Now, of course, you've probably heard about this already as well. There's a lot of coral bleaching going on in eastern Australia, and what it's doing, it's removing some of the algae that would live in the corals naturally, but the temperatures have gotten too high, and the corals are actually expelling the algae. And oftentimes, when corals get bleached like that, they become so stressed, in fact, that they die, and it becomes, of course, a rock. Then at some point, but it's another story of climate change. It seems to be a theme here, isn't it? Well, geologists study climate change. We especially study ancient climate changes, but we're also interested in figuring out what happens in the more recent climates. During the Holocene, we call this. So everything over the last 12,000 years. Well, since the lakes disappeared from the Sahara, right? So the last 10, 12,000 years, a lot of changes have happened. So we do this. We start this way. We look at rocks in general, right? But, we can understand rocks based on the things that we see in today's world. We use, in other words, analogs to try to understand the world. And we propose ideas. Now, there's still a few geologists that do experiments and things like that, but much of it's very much observation-based. And so we look at rocks. And so when we look at rocks, first question we always ask is, what is that? And that's going to be what you're going to be asking when you look at the minerals to begin with. And so you're going to look at minerals, and then you're going to look at rocks. I think maps may be first in lab, but maps, and then minerals, and then rocks, and then you're going to look at more rocks, and then you're going to look at more rocks, and eventually you're going to look at things like geologic structures and things like that. But this is just kind of an introduction to what you're going to be doing the rest of the semester in here. And it's exciting if you really want it to be exciting, so it's kind of neat. Everything that we have on Earth comes from somewhere, and so we'll talk about minerals next. We're going to talk a little bit about chemistry, but then we're going to talk about how elements can combine with one another, or maybe not combine with one another, and form minerals. And so those minerals are going to be the next stop along our geologic passage as we go along. So anyway, thanks for your attention, and we'll get back to this work here in just a bit. Thanks a lot. Bye now.